Hi everybody, and welcome to the first video of notes of the year. Whenever you watch these videos, make sure you have a notebook and a pen or pencil and your graphing calculator handy, so if you need any of those things, just pause the video quick and grab them. Also keep in mind, these are your notes, so rather than me standing in class and writing it as you copy, this is replacing it. So make sure everything that's written down on the screen here, you're writing down in your notebooks for your reference for later on. Also, keep in mind that this video may only be 5 to 10 minutes, but as you go through, it might take you 10 to 20 minutes, maybe even 25 minutes to write everything down and digest it. So don't mindlessly go through this. Keep in mind this is taking place of in-class instruction. The next day we'll always have time for questions, but make sure you're not just zoning out and copying down the notes. So this video is just a brief overview of limits 3 ways. So limits, we're not going to spend too much time on, but I want to just do one last overview, looking at limits graphically, numerically, and algebraically. All 3 of those are assessed on the AP exam, so I want to make sure you're comfortable with them. We're going to take the function x cubed minus 8 all over x minus 2. Now this looks like a rational function because there's an x in the numerator and denominator. And what we're going to do is we're going to find the limit of it as x goes to 2. So we want to know what y value the function approaches when x approaches 2. So what does y intend to be? It might not actually reach that value if there's a hole there or there's a jump discontinuity there. Whoops. But we want to know, what does y intend to be? Now, the first thing we should always try when we do a limit is substitution. If you do substitution, notice that we get 0 over 0. That is indeterminate form, so that means we can't get the limit from it. Anytime you have 0 over 0, that means you have a hole in the graph. So later on, algebraically, we will fix the problem. But for now, we still don't know what the limit is. The function is undefined when x is 2. So we're going to graph this thing. So go on your graphing calculator and type in, go to y equal, and type in your function x cubed minus 8 divided by x minus 2. Now, for now, I'm going to do zoom standard, just to see what's going on here. And notice that our graph does not look rational at all. It looks like a parabola. That's because later on you'll see that the denominator cancels out and it doesn't end up looking like a rational function anymore. Now, I want to know what's happening when x is 2. So I'm going to go to my window. So go to your window with me here, and let's fix a couple of these. Let's make x min negative 5. We don't need to go all the way to negative 10. Come on. And let's make the y min negative 5 as well. We don't need to go all the way down there. I'm going to make the y max, let's make it 15. That way we can see around x equals 2 easier. Alrighty, so it doesn't look like there's a hole in the graph whenever x is 2. Remember, the calculator at this point is not really going to show it. You'd have to zoom in a lot, and then it will show a tiny little gap. If I trace this, and let's find my cursor here. I'm going to move my cursor, so do this with me so you can actually see it. So it's better when you do it yourself. So, alright, I am going to look at my x values, and I'm going to move them closer and closer to 2. And again, we're noticing what y wants to become. Remember, a limit is a y value. So I'm moving to the right. My x's are getting closer and closer to 2. We're getting closer here. Notice your y values are increasing. When I'm at 1.93, I'm at 11.59. All of a sudden, I jump to 2.04, and I'm at 12.27. If you keep going further away, it increases. If you approach 2 from the right and you come this way, you can see the y values are decreasing. So we could guess the limit might be 12, but this isn't very accurate because the change in the x values it doesn't seem like a lot, but we want to get even closer to 2. So graphically, we might think it's around 12 or close to 12. So what we're going to do, and I want you to do this in your notes here, is draw the graph. We know that the limit looks like it's approaching 12. 10, 12. Right now, I'm going to just go ahead and tell you it is 12, just so you can actually graph it. We're going to make that a little more accurate in just a second here. So this is just a sketch. It doesn't have to be perfect. And it looks something like that. The most important thing is a hole in the graph right here. I could make that look a little nicer. Hopefully yours turned out a little bit nicer than mine. So if we trace the function close to x equals 2, we can see the y values are approaching 12. So right now we are thinking the limit is 12. Let's be a little more accurate here. We're going to do it numerically using a table. So we're going to use a calculator to help us, because what you could do is take your x values and plug them into your function one by one. But this is a shortcut you're going to want to start using. Let's do 1.75 here. I'll do one of them with you and have you do the rest. Okay, so what I'm going to do is I'm going to make sure it's still on trace. And I'm going to type in 1.75. Some of you already do this if you're not aware of this. This is a way quicker way to evaluate a function. You get 10.5625. So what you'd want to do is write in 10.5625. So pause the video, copy this table down, take a minute, and type in the rest of the x values to get y values. And you should notice a lot better, should be way more accurate, that as you approach 2 from the left and from the right, the y values approach 12. At 2, it's undefined. So pause the video and do that. Alright, so once you're done here, hopefully you did this, these are your y values. As you can see, coming from the left, coming from the right, we can really see now that the y values are very, very close to 12 exactly on both sides. So it looks like y is intending to go to 12. So even though it's undefined at 2 and it never actually reaches 12, the numbers are getting very, very close to it. So I would pause the video and write down these notes before we move on to the algebra. Let's go ahead and do that. The third way, algebraically. So the table makes it very clear that we are getting close to 12. Algebraically is the most concrete way to see. We want to verify the limit actually is 12 without needing a table or a graph. Now our function was x cubed minus 8 all over x minus 2. Think back to Algebra 2 when you did factoring. This here is a difference of 2 cubes. So this is the actual general formula that we're going to use. Remember, when you have two numbers that are cubes, you could have a sum or a difference. In this case, when I write it, my a is my x and my b is 2. So when you plug in, you get this. And that's very important because you can't get rid of the 0 over 0 problem unless you can cancel something. And you can't cancel something until you factor your numerator. So make sure that's written down in your notes. When you're all set, go to this here. Alright, so I'm continuing on here. I have the limit as x approaches 2 of my original. That is equivalent to the limit of this. I wrote the factored form of the numerator. Notice that this cancels, so write this down in your notes here. The work. That's messy. Alright, cancels. Now, after it cancels, we're left with a quadratic here, with a y-intercept of 4. So that's why our graph looks like a parabola, because all we're left with is a quadratic. Now we're going to try substitution again now that we got rid of this problem, the x minus 2. That's gone. Once you use substitution, and you're actually plugging the x value in, you don't need to write LIN anymore. So whenever you're showing work on the AP exam or on any test or quiz, you're going to want to show work and you're going to want to make sure you're precise on when you need to write this and when you don't. At this step, you don't need to write it anymore. You plug it in and you get 12. So graphically, we thought it was 12. Numerically, it was very clear it was 12. And algebraically, you can see it definitely is 12. So make sure that's all written down because very soon in class you're going to get a worksheet practicing all three methods with 8 or 9 different functions, and this will be your reference.